Good morning and welcome. We will continue today with our discussion on Newton's divided differences and how to use it to derive the B-spline basis functions. A quick recap on what we did previously: divided differences and B-spline basis functions. So previously we studied a truncated power function. F of t sub j colon t is equal to tj minus t truncated raised to m minus 1. This function is a pure polynomial tj minus t raised to m minus 1 for values of t smaller than tj. That is, for this value here, positive. And this function gets truncated, implying that the value of this function is 0 for values of t greater than tj. This is how this function looks like. For values of t smaller than tj, the function is a pure polynomial of degree m minus 1, and for value of t greater than tj, the function is truncated to have a 0 value. So if tj colon t, which is tj minus t truncated raised to m minus 1, is continuous at t equals tj right here, and so are its derivatives up to m minus 2. Recall the definition of a spline curve. An nth order, which is an n minus 1th degree curve, is a spline if the curve is c n minus 2 continuous everywhere in the domain. By this observation, the truncated power function is a spline, and it is a spline of order m. We had also made a proposition with regard to B-spline basis functions. Let's revisit that again. Since each truncated power function is a spline, it is natural that their weighted linear combination, which is summation r going from 0 to n alpha r tr minus t truncated raised to m minus 1, we call this function psi of t, is also a spline of order m. And so we had mentioned that a B-spline basis function is the mth divided difference of the truncated function f s colon t, which is equal to s minus t truncated raised to m minus 1. The trick here is to hold t as constant and compute the divided differences with respect to s, and introduce knots accordingly. And it was this way of computing B-spline basis functions that we thought would be worthwhile to exploring. We'll do so in today's lecture and a few more. As I had mentioned before, we might want to treat t as constant and compute the mth divided difference using s as t I minus m, t I minus m plus 1 up till ti. Using the algebraic form, this divided difference will look like psi of t is equal to t I minus m minus t truncated raised to m minus 1 over w prime at ti minus m plus t I minus m plus 1 minus t truncated raised to m minus 1 over w prime t I plus 1 minus m, and the last term in the summation would be ti minus t truncated raised to m minus 1 over w prime evaluated at ti. Here w is the product of t minus ti minus m, t minus t I minus m plus 1, and so on up till t minus ti, and w prime is the first derivative of w with respect to t. We delved into this expression further, and we showed that psi of t is 0 for values of t greater than ti and for values of t smaller than ti minus m. So this knot on the right is ti, and this knot on the left is ti minus m. So for t greater than ti, psi t is 0, and that is because ti plus r minus m minus t truncated raised to m minus 1 for r going from 0 to m are all 0. This is because each of these terms, they become negative, and it's because of this truncated sign here that all these terms, they individually become 0. For values of t smaller than or equal to ti minus m, again psi t is 0. This is because psi t is the mth divided difference of a pure m minus 1 degree polynomial. We have seen a few examples in previous lectures, and we have shown this to be true. Also, psi of t is standardized. We showed this using the Peano's theorem that says factorial m minus 1 times the mth divided difference of any function g is equal to integration from ti minus m to ti psi of t times the mth derivative of g times dt. We chose gt to be equal to t raised to m. So the mth derivative of gt is factorial m, and the mth divided difference of t raised to m is 1. Plugging these information into Peano's statement, we can see that m minus 1 factorial is equal to m factorial times integration from ti minus m to ti of psi t dt, which implies integration from ti minus m to ti of psi t dt equals 1 over m. And this is the standardization condition for a B-spline basis function. All we need to do is to show that psi t is non-negative for values of t in between ti minus m and ti. We'll show that a little later. We continue with our discussion on B-spline basis functions, and today we'll try to derive the recursion relation for that. This is lecture number 23. A lot of books directly start with the recursion relation. We'll try to prove the recursion relation for B-spline basis functions. We start with Leibniz result. How do we compute the divided differences of the product of two functions? Say ht equals ft times gt. Leibniz result states that the kth divided difference, that is h within square parenthesis t0, t1 up till tk, is equal to summation r going from 0 to k, the rth divided difference of f, which is f within parenthesis t0, t1 up till tr, times this divided difference here of the function g, represented by g within parenthesis tr, tr plus 1 up till tk. I'll not prove this result for now. Although this result is true for a generic case, I'll show that this result holds for the first few cases. So h of t equals f of t times g of t. Let's look at what h t0 t1 is. By definition, it is defined as h of t1 minus h of t0 over t1 minus t0. This is equal to f of t1 g of t1 minus f of t0 g of t0 over t1 minus t0. I'll add and subtract one term here. I can write this thing as f of t1 g t1 plus f of t1 g of t0 minus, I'll subtract the same term here, f of t1 g of t0, and I'll borrow this term from here, minus f t0 g t0 over t1 minus t0. Now what I'll do is I'll take f of t1 common in between these terms. So f of t1 g t1 minus g t0 over t1 minus t0. I've taken care of this term and this term. And here I have g of t0 common. This would be plus g of t0. What I am left with is f of t1 minus f of t0 right here over t1 minus t0. Notice what gt1 minus gt0 over t1 minus t0 is. Likewise, what is f of t1 minus f of t0 over t1 minus t0? We have f of t1. This is the first divide difference in G. This would be G t0 t1 plus, here we have gt0, and here we have the first divide difference in F. And this is what the Leibniz result predicts for the first divide differences of a function ht that can be represented as a product of f of t and g of t. Let's see if Leibniz result gives the correct prediction for the second divide difference. So ht equals ft gt, and we are looking at what h t0 t1 t2 is. To make my algebra a little simpler, I'll introduce a shorthand. So what I will do is I'll represent the second divide difference h t0 t1 t2 as h sub 0 1 2. Now, by definition, H T0 T1 T2 or H 0 1 2 is equal to H T1 T2 minus H T0 T1 over T2 minus T0. Using the shorthand notation, this is H12 minus H01 over T2 minus T0. The Leibniz result gives accurate predictions for the first divide difference. So I can substitute for H12 in terms of the divided differences in F and G. So H012 equals, now what is H12? H12 will be F1 G12 plus F12 G2 minus what is H01? This would be F0 G01 minus F of 01 G1 over T2 minus T0. Can I simplify this further? Maybe I can. I'll have to add and subtract a few terms. Let's say I add plus F of 0 G 1 2. Now what I intend to do is I intend to extract the second divide difference in G, and that's the reason why I've added F0 G12. I need to subtract the same term F0 G12, and let's see what happens. If I combine these two terms, what do I have? I have F of 0 G 1 2 minus G 0 1 over T2 minus T0 plus 1 over T2 minus T0 times whatever is left, F1 G12 plus F2 F12 G2, this term here, minus F01 G1 minus F0 G12. What is this term here? This is the second divide difference in G, if you notice. So this is equal to F of 0 G 0 1 2 plus 1 over T2 minus T0, this entire term here. Let me rewrite this for you. F1 G12 plus F12 G2 minus F01 G1 minus F0 G12. what is next? Now let's see if I can further simplify this expression. Let's figure if anything is common out here. I see that there is one term G12 here, the first divide difference of G, and G12 here. Maybe I can take this common and I can write this thing as equal to F0 G012 plus 1 over T2 minus T0 G12 F1 minus F0. I have taken care of this term right here and this term right here. What I'm left with is plus f of 1, 2, G2 minus f of 0, 1, G1. Now, if I notice this expression, I can see the first divide difference in f getting filtered out. So, this expression becomes F0 G012 plus G12 F1 minus F0 over T2 minus T0. I multiply and divide by T1 minus T0 here. This is T1 minus T0 over T1 minus T0. What am I left with is 1 over T2 minus T0 f of 1, 2 G2 minus f of 0, 1 G1. This is F0 G012 plus G12 F1 minus F0 over T1 minus T0 is the first divide difference in F. I can write this thing as F01 times whatever is left, T1 minus T0 over T2 minus T0 plus 1 over T2 minus T0 F12 G2 minus F01 G1. What do we have? We have F0 G012 plus some constant times F01 G12, and what are we looking for? We are looking for F012, that is the second divide difference in F. How can we extract the second divide difference in F? F012. I would need to add and subtract something else here. What I'll do is I'll add G2 F01 and subtract G2 F01, and let's see what happens. These two terms are within these parentheses. So H012 equals F0 G012 plus F01 G12 T1 minus T0 over T2 minus T0 plus, let me combine this term and this term. What would this give me? This would give me G2 F12 minus F01 over T2 minus T0 plus 1 over T2 minus T0, whatever is left. So I had considered this term here and this term here. What I'm left with is G2 minus G1 F01. If you notice, F01 is common in between these two terms. I should be able to simplify matters a lot from here. This is F0 G12. There will be 0 here. So F0 G012 plus F01 G12 T1 minus T0 over T2 minus T0 plus, what is this? This is G2, the second divide difference in F, F012 plus, I can simplify this further. This is F. I can multiply and divide by T2 minus T1. When I do that and I simplify this a little further, this would be G12 times T2 minus T1 over T2 minus T0. Now concentrate on these two expressions. F01 G12 is common. So this is F01 G12. T2 minus T0 is the common denominator. We have here T1 minus T0 plus T2 minus T1. What am I left with? I'm left with F0 G012 plus I'm left with G2 F012. If I simplify this factor further, T1 cancels out, T2 minus T0 cancels out with T2 minus T0 here. So this term is equal to 1. So finally, H012 equals F0 G012 plus F01 G12 times 1 plus G2 F012. So if I let go of the shorthand notation and if I expand this using the convention that we have followed for the divided differences, this is H T0 T1 T2. This is equal to F T0 G T0 T1 T2 plus F T0 T1 G T1 T2 plus F T0 T1 T2, which is this term here, times G T2. this is what is precisely predicted by the Leibniz result for the second divide differences. Although I was quite elaborate in my algebra when showing the Leibniz result to be true for the first and the second divide differences, in H, I am not sure if that would be the best way to prove the general result. You can look into much elegant proof by searching through the net. For example, I went through the Google website and I found this paper, A Remark on Divided Differences by E.T.Y. Lee. This paper presents a much elegant proof of the Leibniz result. You might want to take a look. However, here our intention is different. We are going to be using this result to derive the recursion relation for B-spline basis functions. Anyhow, the general result H within parenthesis T0, T1 up till Tk, if I expand this summation here, I get f of T0 times g of T0, T1 up till Tk plus f of T0, T1 times g of T1 up till Tk plus a few more terms, and the last term would be the kth divide difference in f and the 0th divide difference in g evaluated at t sub k. Now, to be able to use this result and derive the recursion relation for B-spline basis functions, all we need to do is use h of k of t sub j colon t, which is our truncated power function of degree k minus 1, tj minus t truncated raised to k minus 1 is equal to tj minus t truncated k minus 2 times tj minus t truncated. So what I have done here is I have expressed h of k, which is our k minus 1 degree truncated function, into a multiplication of two functions. One is a truncated function of degree k minus 2, and the other one is a truncated function of degree 1. I write this thing as h sub k minus 1 tj colon t times tj minus t truncated. Try to relate this h with this h here. K is a subscript introduced simply to denote the order of the truncated function. So the degree is k minus 1, the order is k, which is represented by the subscript. Now, using hk tj colon t equals hk minus 1 tj colon t times tj minus t truncated. So hk minus 1 tj colon t, you can think of that function to be f of t, and tj minus t truncated, you can think of this function to be g of t, and apply the Leibniz result, and we'll see how we will get the recursion relation from here. Okay, so h of k tj colon t is equal to h of k minus 1 of tj colon t times tj minus t truncated. Let's try to apply the Leibniz result. remember what I said about B-spline basis functions in terms of the divide differences. A B-spline basis function would be the kth divide difference of this truncated function, or degree k minus 1. Let's try to compute the kth divide difference of hk tj colon t. Again, I'm going to be using the same convention that I have been using before. I'll denote the last knot by ti and the first knot by ti minus k. So the kth divide difference of h of k is represented by ti minus k plus 1, and so on up till ti colon t. And this would be equal to h of k minus 1 within parenthesis ti minus k plus 1 up till ti minus 1 colon t plus h of k minus 1 ti minus k plus 1 up till ti colon t times ti minus t, which is a regular linear polynomial. I have skipped a few steps here. Let me show you those steps on the board. So let's start with our truncated power function of order k. And let me represent using two parameters s and t. This is equal to s minus t truncated raised to k minus 1. Now, a B-spline basis function is the kth divided difference of hk s colon t. We have made this proposition before, and we have shown that this is indeed true. Let me go back a little bit, and let me rewrite this thing as s minus t truncated k minus 2 times s minus t truncated. So I can write h sub k s colon t in terms of the product of two functions. This is equal to h k minus 1 s colon t times s minus t truncated by the notation that we use here. So this represents the k minus 1th order truncated power function. Now let's concentrate on this proposition a little bit. B-spline basis function is the kth divide difference of h sub k s colon t, truncated power function of order k. How do I write the kth divide difference of hk? We can use the algebraic form. Psi t, and I'm going to be introducing a subscript here to represent the order of the B-spline basis function. This is equal to hk ti minus k plus 1 up to ti colon t. And using the algebraic form, This would be equal to Ti minus k minus t truncated k minus 1 over w prime evaluated at Ti minus k plus Ti minus k plus 1 minus t truncated raised to k minus 1 over w prime Ti minus k plus 1 up till Ti minus t truncated raised to k minus 1 over w prime Ti. Let me make matters a little simpler here. I'm not very much interested in the values of these denominators for now. So let me replace the denominators by known constants. So psi k t equals alpha I minus k T I minus k minus t truncated k minus 1 plus alpha I minus k plus 1 T I minus k plus 1 minus t truncated k minus 1 plus alpha I Ti minus t truncated raised to k minus 1. This is what I'm interested in. Alpha I minus k plus 1, all these constants over here are respectively 1 over w primes. Let's block this result. As we are going to be using it a little later. Let us go back to this expression here. H of k s colon t equals h of k minus 1 s colon t times s minus t truncated. And using the Leibniz result, let's try to compute the kth divided difference to get a B-spline basis function on the left hand side. How do I do this? So using Leibniz result, the kth divided difference of h sub k, I can write this thing as Ti minus k Ti minus k plus 1 up to Ti colon t. This is equal to, and I can use the Leibniz result directly on the right hand side. Let me call this f of t and let me call this g of t. So in terms of f and g, I'll have f of Ti minus k g Ti minus k Ti minus k plus 1 Ti plus f Ti minus k Ti minus k plus 1 times g Ti minus k plus 1 Ti plus many terms, and the last term here will be f Ti minus k Ti minus k plus 1 Ti G Ti. Now let's try to relate these divided differences with the truncated power functions here. F of Ti minus k is the 0th divided difference of which k minus 1. G of Ti minus k, Ti minus k plus 1 up till Ti is the kth divided difference of S minus T truncated. How about the second term? F of Ti minus k, Ti minus k plus 1 is the first divided difference of which k minus 1 S colon T. G of Ti minus k plus 1 up till Ti is the k minus 1th divided difference of S minus T truncated, and so on until we get the last term here. F of Ti minus k, Ti minus k plus 1 up till Ti is the kth divided difference of H of k minus 1 S colon T, and G Ti is simply the value of S minus T truncated at S equals Ti. In this result, not all terms will be important to us. In fact, it will so happen that only the last but one term and the last term will be non-zero, and all the other terms will be 0. At this time, I'll agree with you that this is looking way too complicated. But if you hang in there with me, I think I would be able to simplify this expression a lot better.